Hello, this is a space elevator, which is an actual idea for low-cost deployment of spacecraft. Rather than having to use an engine, you do the bulk of the work by putting spacecraft along the cable, perhaps by a pulley system or something, and then there's less work to do when they get to the end. And you don't need to spend it on rocket fuel. You could use electricity or something instead. Anyway, the first bit says the total length is 58,000 kilometers. The geostationary radius is 42,100 kilometers with an altitude of 35,700. So this bit here is 35,700. And this bit sticking out of the end here is the difference, 58,000 minus 35,700, which is 22,300. Now we can take, it says take moments about the center of mass. I want the center of mass to be at geostationary radius. And imagine that there's the counterweight has a force acting down here, a weight acting down here. I know it's not actually, gravity isn't acting in that direction, but this is my sort of pretend seesaw question. And then I take the center of the cable, which is around there, and I give that a weight too. Now I've got to work out these two distances. Now I know the center, I know the distance to the center of the cable. That's just 29,000. So I can work out that bit in there. That's going to be 6,700. And this bit here, that's the same. That's still 22,300. So now it's just a moments question. And I need to work out the mass of the cable as well. So let's just put that up here. That's going to be the length of the cable, which is 8 grams per meter or 8 kilograms per kilometer. And I'm going to multiply that by the length. So 8 times 58,000, which is 464,000 kilograms. Now, I can work out the counterweight because let's call it M. So taking moments, 22,300 times M, that's going to equal the moment on the other side, which is 6,700, the distance from the pivot, multiplied by the mass of the cable, which is 464,000. That will give me the mass of the counterweight, which is that answer there. Just plugging that into my calculator. And that gives me 139,408 kilograms. That's the mass of the counterweight. Now add those two together and we'll get the total mass of the cable plus the counterweight, which is 603,408. And we know that the center of mass of those two objects must be located at the geostationary radius. How much gravitational potential energy is needed to put the space elevator into orbit? Well, be careful here, because we're taking the material from the surface of the Earth. So for that question, it's a change in gravitational energy, which is a change in Gm over R. Now G isn't changing, big M isn't changing, little m isn't changing, but just it's 1 over R1 minus 1 over R2. And those two radii are the radius of the Earth, 6,400, and the radius, the geostationary radius. Running a bit out of space here. So I'm going to do it up in the top left. So that's just 6.67 times 10 to the minus 11 times the mass of the planet. It's just the Earth, I suppose. So 5.97 times 10 to the 24, which is at the bottom there, times the mass of the cable, which is 630,408 kilograms. And I've got to multiply that by the difference in the two radii. The radius of the Earth is 6,400 kilometers, which is 6.4 times 10 to the 6 meters, and that's to the minus 1. And I take that away from the geostationary radius, which is 42,100. So 42.1 times 10 to the 6 to the minus 1. Plug that whole thing in, 6.67 e to the minus 11 times 5.97 e to the 24 times 603,408 times 6.4 times 10 to the 6 to the minus 1 minus 42.1 times 10 to the 6 to the minus 1. And that gives me a huge number, 3.2 times 10 to the 13. So it's a lot of energy. And the last bit now, the kinetic energy needed in order to keep it moving with the Earth. Well, the shortcut here, hasn't got much to do with a half mv squared. The kinetic energy in orbit is a half of the gravitational potential energy at that radius. So that's going to be a half of the gravitational potential energy at geostationary radius. I'm going to have to clear a bit more space somehow. Gosh, where am I going to do it? Oh well, let's crack on. So that's going to be a half times 6.67 times 10 to the minus 11 times the mass of the planet, 5.97 times 10 to the 24, times the mass of the space elevator, and divided by geostationary radius, 42.1 times 10 to the 6. And that gives me 2.9 times 10 to the 12. It's not exactly half of the previous question because we didn't have to move the elevator from the center of the Earth. I suppose it wasn't the center of the Earth, it was from infinity, or either of those. We had to take it from the surface of the Earth.